Okay, good afternoon all. Let's wait for 5 more minutes to see if anyone joins, then we'll start. Okay, So I see nobody has joined. No issue. The recordings will be available. Let's start. So this is NPTEL NOC EE-62. This is a tutorial session for the course Basic Electronics, where the instructor is Professor Mahesh B. Patil from IIT Bombay. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar. As you know, this duration of this course is 12 weeks, and we go live for this tutorial session every Sunday from 3 to 5 p.m. There are certain prerequisites, as I have been iterating it several times. So I expect that you at least have gone through all the problems and attempted all the lecture videos posted on the course web page, and at least attempted the assignments once. It will help you to grasp the concepts and the problems that are solved here in this tutorial session. And as far as the decorum is followed, please ensure that your microphones are muted all the time, and you can use the raise hand option to ask any query. And also, after each topic or problem I solve or cover, I will provide you certain time to ask your doubt. And also, as it is a 2 hour session, at the end of 2 hour, I will give you 10 minutes time. I generally see it is not possible. So if I have time, I will discuss some topic extra, maybe, which will be helpful to you, or I will give you some time to ask a general query regarding the session, right? Also, I request you to keep a scientific calculator handy all the time during the session so that you will get to do the problem solving along with me, right? The links will be posted on the YouTube channel, and I think the link has been shared to you by the NPTEL team. Okay, so let's begin. So this is week 6. We are at the halfway to the tutorial sessions. This is 12th March. So let's begin. So as far as the problem number 1 goes, it is said that let A1 be a common emitter amplifier with a resistance RE completely bypassed. RE means here they are referring about emitter resistance, right? Let A2 be a common emitter amplifier, RE equals to RE1 plus RE2. Sorry, where only RE2 is bypassed. Bypassed mean, it is being bypassed by the bypass capacitor. All the other parameters are identical to A1 and A2, identical in A1 and A2. Which of the following statements is true? First, let us draw the amplifier, right? So, as you know, let us draw a simple topology for the amplifier. This is, let's say, it is biased with voltage divider configuration. From here you are taking your output. This is your load resistance. This is your coupling capacitance. This is RC, let's say R1 and R2. And you apply your input. Here is your VCC. And let's say you apply your input signal here. This is your coupling capacitance to the input side. And you have this is your RE, and this is your CE, right? So let's say this one is your A1. This amplifier topology is your A1. Okay. It is mentioned that it is completely bypassed, right? And in another case, what happens that, let me, this portion is replaced as CE is connected like this, right? This is your RE1, this is your RE2. Okay, and here is your remaining of the circuit. So it is asked that, let me clarify it, RE2 is bypassed only, yeah. So it is asked that how will you go about this circuit, okay? So if I draw the small signal equivalent of, let's say this is your A2, right? Of A2. How will it look like? You know that the transistor will be simply this contraption where this is your R pi, this is your VBE, and this is your GMVBE, right? Then you have your VCC will be grounded, so your RC will be grounded, and this is your RL, this is your V naught. So I am assuming that, I think you are aware that this capacitance is shorted, because I am assuming that the capacitance and omega c is such that it provides very low impedance, right? So I can assume it to be shorted. Okay, this is as far as output side is concerned. And for the emitter part, let me draw it clearly. This is your RE1, this is your RE2, this is your CE, right? And for the input side, what happens? That you will have a equivalent resistance here. This is your R1 parallel R2. Let's call it RB. Let's call it RB. And this capacitance is also like it will be treating, we will treat it like a short, and there is your input signal. Okay, so there is your capacitance, here is your capacitance, and we'll see about how to go about this emitter capacitance, right? Okay, so this is your common emitter configuration. Now the question is, I have two cases. One case is that this is my A1 configuration, right? This is my A1 amplifier. What will happen in this case? In this case, at AC signal, my capacitance will be short. So I will have a short path from, this is your emitter, this is your collector, this is your base, right? So I will have a short path, so I can neglect this. So I will simply have this contraption, right? For A1, I will simply have a ground connection, right? Let's change it to A1. And what about A2? And if I look at A2, then I see that I have, you notice it, that I have only this capacitance bypassed, right? So RE1 will be there, and there I will have this ground. So if I draw it properly, it will be RE1, right? And this is your A2 amplifier. So what I will do, I will analyze this A2, and after the results we got, we would get, then I will just replace this RE1 by 0 to get the case for A1, right? So let's proceed with the analysis of this circuit. So what I see, I need to find out two main parameters, right? One is input resistance. Another one is I am interested is voltage gain, right? Voltage gain, that is V naught by Vs, and this input resistance is Rin. So Rin is nothing but resistance looking in this side. Okay, so how to go about it? So as you know, when to how to find this input resistance, I will simply remove this Vs and apply a V test here, and I will check my I test, and the ratio of V test by I test will be my Rin, right? So as you know that is this I test is flowing here and here. This current is my IB and this current is my IE. So IE I can write as IB into beta plus 1, right? Because your IE is IC plus IB, I beta IB plus IB, that is your beta plus 1 into IB, right? So what happens actually, this is your total I test, right? So if I write the I test, or let me go about it in this way. So V test by I test, I can directly write as R in, that is your this RB, which will be this RB I am seeing here, and this is a parallel contraption with this entire thing, right? And that is RB parallel your R pi plus, you see the same current, if you consider the same current is flowing, then your RE1 will be multiplied to B plus 1, right? To account for the voltage drop across this point and ground, right? So this will be R pi plus beta plus 1 into RE1, right? So this is your input resistance for amplifier A2. Okay, what about A1? For A1, you just simply put RE1 is equal to 0. That will lead to Rin is equal to RB parallel R pi, right? Now, can you tell me which one is more for this is for A1 and this is for A2. You can simply see that if I use Y in, that is 1 by R in, is nothing but 1 by RB plus 1 by R pi plus beta plus 1 RE1, right? So if RE1 increases, then if RE1 increases, then my this entire term decreases, right? So if this decreases means this decreases, right? Can anybody unmute yourself and tell me what will be the answer? That whether for whether the input resistance will be greater for A1 and A2? I see two people joined. One is Satish, another one 1093. Can anyone unmute and tell me how will my input resistance change? You see, It is simple, right? If RE1 increases, then this term increases, this term decreases. If this decreases, so this decreases. That means your Y in decreases. That means your R in increases, right? So you see, for input resistance, my input, let us put it in this way, input resistance of A2 will be more than A1, right? Because my RE1 is more in A2, case A2 or amplifier A2. Now, can you comment on the voltage gain? What about the voltage gain? Let me just copy this circuit. So your voltage gain, V0 is nothing but your GM VBE minus of GM VBE, because current is flowing this way, into your this RC parallel RL, right? This is your parallel contraption, and this entire current flowing out of that terminal. So it will be GM VBE into RC into RL. So we need to find out VBE in terms of VI, right? How do we go about it? See, this is your VS, right? So this point will be your VS. So your VS will be equal to nothing but, if I look between this terminal, right? This to this, B to ground. Then I'll see Vs will be my VBE plus your this drop, right? What is this drop? This drop is IE into RE1. Okay. And your IE is nothing but IB into beta plus 1. Okay. How can you find out IB? You know that beta IB is equal to your GM into VBE, right? So you can find out IB as GM VBE by beta, right? Because this current is nothing but your collector current, right? This is nothing but equal to beta IB. So you get VBE plus your IE is nothing but beta plus 1 by beta into beta plus 1 by beta into GM VBE into RE1. Okay. So if we assume beta is much greater than 1, then my this term goes to 1. So your Vs will be VBE 1 plus GM RE1, right? So what about your VBE? VBE will be Vs by 1 plus GM RE1. So again, if I put this in this equation, then V0 will be minus GM RC parallel RL into your VB would be Vs over 1 plus GM RE1, right? So you will have your gain V0 by Vs as minus GM RC parallel RL over 1 plus GM into RE1. Okay, so you see if RE1 is equal to 0, then your V0 by Vs is GM RC parallel RL, right? And if RE1 is not 0, then your overall gain, that means V0 by Vs, reduces. Okay, and this is the case for A1, amplifier A1. So you see that gain, or I should say voltage gain, reduces in case of A2. In case of A2, right? So let us go back and check the options. So A1 has a smaller voltage gain. This is wrong. A2 has a larger DC bias current. DC bias current has nothing to do with this. A2 has a larger input resistance. Did we find that? Input resistance for A2 will be more than A1. Yes. This is one conclusion we drawn. This is the another conclusion we have drawn. So your answer would be this, right? Sorry. Your answer would be B. A1 has a larger input voltage amplitude without causing distortion. This is from the linearity point of view, which has nothing to do with this emitter resistance, right? So you see that you do not need to remember any kind of formulas, right? You simply just remember that how does your this transistor look like, and a common emitter amplifier configuration, you should be very thorough about it, that this configuration looks like this only. So you can simply make this circuit this small signal equivalent, and when you make your small signal equivalent, you should be able to get that. What about this bypass capacitance? Bypass capacitance at small signal sense, you can assume it to be, if nothing is mentioned, assume it to be short. So suppose you have two resistance as shown here, and one part is short, that means this resistance is not valid, is not doing anything in the small signal case. So you have just simply this short connection grounded, right? This is how we get this picture. And then just it is KCL and KVL, right? Which you should be very familiar with. So just by simple analysis, you will be getting these results. And also it should be coming as an intuition that this is the case, this is such the case, right? Because one case you have these two resistances only, this is grounded. Another case there is a resistance is parallel path, one of the branches the resistance is more. Obviously input resistance, as it is a parallel combination of this path and this path, it will be more, right? Similarly, what about the gain? Gain means how will the gain reduce? Simple analysis, simple intuition should be that this current is directly proportional to your gain, right? This currently directly proportional to your voltage, output voltage, because this current is flowing from this parallel combination, out of this parallel combination. So as this current, you need to check whether this current is getting increased or decreased, right? So GM is same, but your VBE, you need to find out that earlier the entire input voltage was falling across this VBE. Now the input voltage is between B and this ground. So input voltage is getting dropped across this RE1 also. But this RE1 will not contribute to your output, this collector current, right? So your effective VBE is getting reduced from the input voltage. So eventually your current will reduce and your output voltage will reduce. That means your gain will reduce. This you can do by intuition also, but in the beginning it is suggested that you go for this circuit analysis, right? And make yourself familiar with it. So now we will be discussing about some op-amp circuits. Okay. So till this point, do you have any question? I see two people, Satish and Farhan. I'll give you 1 minute time, else I'll move on. Okay, I think you have understood the problem. So let's move on to next problem. Let me zoom it up. Uh, in the circuit shown in the figure, the op-amp operates in the open loop configuration. What is the duty cycle? Defined as a fractional. Okay, okay. So see, let me first tell you briefly about what is op-amp, right? When you analyze op-amp circuits with ideal op-amps, right? I will tell you what is ideal op-amp. Then you should be treating it as a voltage control voltage source. This is the simplest way you can treat it. That means suppose you have a this is VA, this is VB, and this is your V out. And let's say op-amp has a gain of A. Then what is your V out? Your V out is nothing but A into VA minus VB. Okay, this is how the op-amp works. Now, how do you know this is a voltage control voltage source? Because this you can treat it as a differential voltage VD. So it is simply a voltage amplifier, right? So how can you analyze this circuit? Say this is your VD and let's say this is not necessarily this is grounded. Let's say this is your A of VD. Okay, this is a VCVS. You must be quite familiar with how to analyze the VCVS circuit. So you can simply analyze op-amp as a VCVS, right? Now that is fine. What is about this open loop configuration? What is open loop and closed loop? I think you guys must have read this control systems, right? So what open loop means, suppose you have a system, this is your input, this is your output, and there is no communication between your input and output. That means your input has no knowledge about how the output is behaving. That is your open loop, right? So, and what about closed loop? Say this is your input, this is your output, and you have a certain feedback path from which you are communicating with your output, right? So that is your closed loop configuration. Generally, we operate closed loop configuration based upon your this sign, generally closed loop can be of two types. One is negative feedback, another is your positive feedback, right? So why do we need for negative feedback? The main purpose of negative feedback is to provide you stability. And where does your positive feedback gets used? It gets used in oscillation, right? To create oscillation, you generally use your positive feedback. Now, so if this is negative, it is negative feedback. If this is positive, then it is positive feedback, right? So why do we need negative feedback? Suppose you are driving a motorcycle, right? And if you are driving a motorcycle and if you do not have the speedometer means the display where you see what is the speed of your vehicle, right? Suppose you do not have that, then how do you know that whether at what velocity you are supposed to go? Suppose you are going at a speed of your 40 kmph, right? Then suppose you have your accelerator, right? You turn your accelerator and you get your speed up. So that is an example of an open loop system. Here you do not have a control that whether you are going at your 40 kmph or you are going at a higher speed, right? So how does the negative feedback come into picture? That suppose you want to maintain a 40 kmph speed in a national highway, because not suppose in a state highway, because the speed limit of that highway is 40 kmph for that particular location. So how do you get ensured about that whether you are getting this 40 kmph speed? So you will be turning your accelerator. Suppose you are starting from zero, from rest, right? 0 kmph. Then you start your accelerator, and after some time you see that you have reached 40, right? But you have some certain inertia, so it will not always remain 40, but you will get some higher value maybe. Suppose you go to 45, then you, after from looking at the speedometer, you will see that you need to reduce your speed. Then you will again turn your accelerator in the opposite way, and you reduce your speed, and in that way you will maintain your speed at a stable velocity of 40 kmph, right? So this here your eyes and your speedometer acts as a negative feedback. So this path is the negative feedback. This path is the feedback path, right? And this path we call as a forward path, right? So given that context, so you understand that for now you understand that negative feedback is required for to maintain your stability, or you to have a stable system, and positive feedback is used sometime and mainly to get oscillation, right? So for and so this is, and what about open loop system? If your system is open loop, that means you do not have this feedback path, right? So in this question it is mentioned that the op-amp operates in a open loop configuration, right? So let's copy this. You can see that there is no direct path from output to input side, right? Neither this way nor this way. So you can get assured that this is a open loop system. Now the question is how to analyze this. Okay, for an open loop system, your output is simply nothing but, if I say this is V plus and this is V minus, is your gain into V plus minus V minus, right? And let's say uh, your input is, let's say for the time being it's A, right? Let's say it's 1 for the time being. Okay. So what is your V minus? You can simply see your V minus is nothing but 3 into 2 over 3, right? That is your 2 volt. This is just simple resistive division. And your V plus is 4 sine omega t minus 1 volt. So your V out is generally this minus this. That means your 4 sine omega t minus 3 volt. Now I need to find out the duty cycle, right? What is duty cycle? Suppose you have a waveform like this. This is T1, this is T2, okay? And the period is T is, let's say period is T1 plus T2, right? So for how much time your signal is on? Your signal is on for T1 duration. So your duty cycle would be T1 by T1 plus T2, right? Generally, it is presented in this percentage format, so you can simply use 100% also if you want to convert it into percentage, right? So this is one way, and now the question is why it is called duty cycle, right? You see, in generally in the factories, or in, if you, simple example I can give you, if you see any security guards of your colleges, right? They generally works in shifts, right? Suppose they have, you have 24 hours in a day and they work in 8-hour shift, right? One person will work for only 8 hours. They have morning shift, day shift and night shift, right? So suppose they work in on one shift, so what will be their duty cycle? Their duty cycle will be nothing but 1 over 3, right? Because they are on duty for 1/3 of the time, entire time. Okay, so their, this duty cycle would be 33.3%. So this is to make sure that you never forget how this duty cycle term come about, and you don't jumble it up with on by off or on by on plus off. What it should be, right? It should be how much time you are on duty, or you, the signal is on over the total time, right? So what about this? How to find out duty cycle of this signal? The way to go about is you simply try to draw a sine curve, right? That this is your, what is the maximum value? Maximum positive value is 1. What is the maximum negative value? Maximum negative value is, for this is -4 and -3, that is -7, right? So let me say, one scale is not up to mark. Let me go and draw it in this way. 1, 2, 3, 4, 5, 6, 7, right? So how will your sinusoidal signal be? This will be between this, right? So what is your duty cycle? This is your zero line. Let's say this is your omega t. So you are on for this much time, right? Let's say for if you are considering one period, then you are on from here to this point, right? This is your 2 pi. This is your pi by 2. And this is your pi, right? So how do you find out what is this point? You need to find out this point, right? So you simply put your 4 sine omega t, 4 sine omega t minus 3 is equal to 0, right? Then what would be your omega t? Sine inverse of 0.75. So that is 48.5 degree, right? So what is your total on duration? On duration is, you know this point, right? But you need to find out this duration. This will be nothing but 90 minus 48.5 into 2. See, this into 2, because this is symmetric around omega t equals to pi by 2. So this is your 82.81 degree, right? So what is your duty cycle? Duty cycle is nothing but this divided by 2 pi. 2 pi is the period of the sine signal. And what is it in degrees? It is 360 degrees, right? And then you use your 100% if you want to get it in percentage. So 360 into 100. So you will have your 23%. So, or you may have it in this also. Point also, right? 0.23 is your duty cycle. So this is the way you calculate your duty cycle, right? You have any question, then we can discuss it again, or else I will move forward to the next problem. This is pretty simple actually, right? So let's move forward to the next problem. Okay, so it is mentioned that in the OPAMP circuit shown what is V naught, right? So how to go about these problems? First thing is, if nothing is mentioned, then you assume your OPAMP to be ideal, right? What do you mean by ideal OPAMP? Ideal OPAMP means is intrinsic gain is infinity. And how does that help? That help in a sense. See, I have mentioned you one thing that this is for a negative feedback system. And why do you need your negative feedback system? To gain stability, right? Now suppose you want an amplifier, right? And you want a particular gain of let's say K. You want your V out to be K of V in, right? How can you go about this? You can simply set it at K, but then if somehow your input gets changed, if you do not have your control over your input, then what will happen? Your output will not be stable. It will start keep toggling, right? And you will not have any information about your output at the input side. So what do you need to do? See, in this negative feedback system, if you have this signal, use a different color. this signal at this point is called a error signal, right? Because it gives you the error between input and what is fed back, right? You want to minimize this error. You want this signal, let's say this is ET, you want this to be 0, right? So how to go about it? What you do is you say you apply, let's say you want your output to be V naught as K times of Vi. So what is your Vi? Is V naught by K. This thing you want to sense, right? So if I feed my op-amp in this configuration, say this is my Vi, and somehow I can make it V naught by K, right? Then what happens? If my output V naught by K, if my input Vi is more than the desired output, or V naught by more than the desired output, more than the desired input, which it should be, that is V naught by K, then let's say if your Vi is greater than V naught by K, right? That means you will drive your V naught up, right? And if your Vi is less than your V naught by K, then your V naught will go down. And how does it work? See, if you increase your Vi, right? If you increase here, that means this V naught will increase, but you want it to be fixed at a particular value, that is your KVI. Somehow, if V naught is increased, then this will also increase, then this will also increase. That means the difference here will get somewhat adjusted to a certain value, or we want it to be 0, right? So let's see how to go about this. You want V naught by K here, right? What you can do, you can simply use a resistive divider. Let's say this is K minus 1, this is K. Let's see some R value, right? This is R. So what is the voltage at this point? The voltage at this point is nothing but your V naught by K. Do you see? This point, this point voltage is V naught by K, and you simply fade it back, right? So if you have any excursion here, this will increase, this value will also increase, and this will try to pull your output down and fix it at a particular value, right? This is how your device works, right? Now let's say this has a value of A, this has a gain of A, right? So what will happen? This your V out will be nothing but A times Vi minus V naught by K. That means your V naught will be 1 plus A by K is equal to A of Vi, right? So what is your V naught? V naught is nothing but AVI by 1 plus A by K. So if I multiply it by K by A, both denominator and numerator, then I will get 1 plus K by A, right? What do I desire? I desire my output to be fixed at KVI, right? For that, from equation, can you see that my A needs to be infinity or very large than K to achieve my V out to be particularly fixed at KVI, right? So generally your op-amps has very high gain, very high A, let's say. That means you can get this operation. This is called negative feedback. This is how you stabilize your output. That's why I told you that negative feedback is essential for you to get this stability, right? So you see, if your A is infinity, right, and you are connected to, and your op amp is connected in a negative feedback, op amp is connected in negative feedback and your A is is very large, let's say infinity, is tending to infinity. So what can you comment between this Vi and V naught by K? What can you comment on this term? This is nothing but your Vd, right? The difference voltage. This will be zero, right? How come? Because if your Vi, if your A is infinity, then V naught will be fixed to Vi into K. That means this point will be fixed to Vi only. That means these are virtually shorted. Vd 0 means virtual short, right? Between the input ports. So what do we see? We see that to use the concept of virtual short, you need two conditions. One, your op-amp needs to be ideal. That means the intrinsic gain of the op-amp should be infinite. That means your ideal op-amp, and your op-amp should be working in negative feedback, right? Now, the question is, the problems which we will be discussing, we will consider the op-amp to be ideal henceforth. Okay? But how do you know that your op-amp circuit is in negative feedback? This point, how will you ensure? Let me tell you a very simple trick, right? Not trick, rather say simple circuit analysis technique. How do you know that your op-amp or any circuit is in negative feedback for that matter? Let's say, let's how to tell whether my op-amp circuit is in negative feedback. Or let me rephrase also. If my op-amp circuit is in negative feedback, then what will be the terminal signs? There is a general conception that if my output is connected to somehow to the negative terminal of the op-amp in the input side, then my circuit will be in negative feedback. But that is not true. I'll show you. That is not true always. Let's do this. Let's say not, let us not first reveal the sign. Let's say the sign is A and B, and you have a circuit like that. Say you have some circuit and you have some voltage source, some current source, okay, and this is your output, okay. So how will you analyze whether this circuit is in, if the circuit is in negative feedback, then what is my sign at A and B, okay. What is the first step? Step 1, remove the op-amp and apply V-test at output. What do I mean by that? This is AB, so this voltage, let's say VAB, okay. So I will apply a V-test there, V-test, okay. So let's say this is Vs, this is Is, and let's also assume that this network is linear. So what can I comment about VAB? I can write VAB as alpha of V-test plus beta of Vs plus gamma of Is, because it is a linear network, right? So as you have rightly guessed, my step 2 would be, see, I do not want these terms, right? Because this does not take any part in the feedback. So I will just make Vs equal to 0 and Is equal to 0. This is similar to nulling your independent sources, right? So what we will have, this goes away, this becomes a short, this becomes open, right? So your VAB becomes simply alpha of V-test, right? Now, if alpha is greater than 0, right? Then your A has to be negative and B has to be positive for negative feedback. If alpha is less than 0, then the opposite way for negative feedback. Okay, note this point very carefully. I will show you with some examples. So let's discuss on this circuit only. So I need to find out whether this circuit is in positive feedback or in negative feedback, right? So let's me copy some box. So let me remove the op-amp and the step 1, and I want to know what about these signs, right? So what I will do, I will apply a V-test here, okay, and I want to see what is the feedback at this point, right? This I will ground, this I will ground, or let me just copy this. Where did it go? Okay, so this I will ground, this I will ground, and I see that anyhow you can simply see it is nothing but a voltage divider, right? These things are parallel. So if I see, if I need to find out this voltage, and this will also be grounded, right? This is grounded. Where did it go? This is grounded and this is also grounded. So I can simply just make a ground here, right? So your VB is 0 and your VA will be, this is your V test, and this has a series this is a one parallel to, what is that? That is your 2 over 3, that is 0.67, and so your VA will be V test into 0.67 by 2.67, right? So basically your VAB will be same. So this is your alpha. So your alpha is more than 0, right? Is greater than 0. So for the circuit to be negative feedback, my A terminal should be negative and my B terminal should be positive, right? This statement. And was it so? Yes, I can see that A was negative and B was positive. So I can simply say that circuit is in negative feedback, right? This way you can check whether your circuit is in negative feedback or not. This is a very useful tool to have. So I see that my circuit is in negative feedback and also my circuit, my op-amp is ideal. I assume that my op-amp is ideal because nothing, no gain is mentioned in the question. So now what do I need to find out? I need to find out what is my V out, right? So let me copy this circuit again. And what is the consequence of having negative feedback and ideal op-amp is that my input terminals are, what happened? My input terminals are virtual short, right? The consequence is that this is in negative feedback we have shown, and also we have shown that this circuit is, this op-amp is ideal. We have assumed that this op-amp is ideal. That means this point and this point potential are same. That means these points are virtual short, right? What is this potential? This is nothing but zero point 0.6 into 1 over 3. That means 0.2 volt, right? So potential at this point is 0.2 volt. So I can simply assume that's virtual short condition. So this point is also zero point 0.2 volt, right? If this point is 0.2 volt and this is 0.2 volt, that means this path does not exist, no current inflow, right? So my circuit is nothing but simply, this is my V out, this is 2K, this is 2K, this is minus 0.5 volt, this is minus, this is plus, and this point I know is it to be 0.2 volt. So this is also 0.2 volt, right? So I know that for an ideal op-amp, no current go inside this terminal. So this current will flow simply here. So I can use KCL at this node. What will I have? Minus 0.5 minus 0.2 by 2K is equal to 0.2 minus V naught by 2K, right? So 2 goes away. Your V0 is nothing but 0.9 volt. So can I see any answer? 0.9 volt? Yes, A is the right option. This is how you go about it. But you need to remember always that you will be checking whether your op-amp circuit is in negative feedback or not, right? Then only you will forward for these conditions, this virtual short condition, and your op-amp should be ideal enough, or your gain of the op-amp should be large enough so that you can assume the virtual short condition. So moving on to before moving on, let me just tell you one more thing. Suppose you don't want to go about this much trouble of finding out how my circuit is in negative, whether my circuit is in negative feedback or not. So how to go about that? You simply just check. Let's say let's say you have some input here, you have some voltage here, right? Some loop here. We have. How will you check whether my circuit quickly? How will you check whether my circuit is in is in positive feedback or negative feedback? You simply break the loop, right? You see the feedback path, you break the feedback path at any point. You increase some potential here, not here. Suppose you push the negative, you pull the negative terminal potential higher, right? If this is higher, that means the difference VD will be lower. That means your V naught will be lower, right? If V naught is lower, this V naught is coming into this only, right? So this will be lower. So you see, by increasing or by giving some voltage increment at certain node, if you go around the loop, you will find that the way the circuit is designed, that the same voltage is pulled down again. Okay, so this way you can see that it is a negative feedback operation. And similar way, if suppose I have a -3 gain amplifier, okay, let's say -3 is the gain. I can have a minus gain of -3. Suppose let me use a different color. Suppose it is -3, right? Then if I give a positive excursion here, this will go down. If this goes down, then -3 gain, this will go up, and I will have more voltage going up, right? So this will lead me to a positive feedback. So you see, by having the feedback path in the negative terminal only, I can make my circuit work as in positive feedback or negative feedback. It all depends upon how much phase shift is there between the input and the output, right? So you do not ever blindly tell that if my circuit is connected to the negative input term, the feedback path is connected to the negative input of the op-amp, then my circuit is a negative feedback. That is not true. It assumes that there is no phase shift in the feedback path from output to the negative feedback, negative terminal of the input, right? So you see, at the negative terminal also I can have positive feedback, just provided that I have a 180-degree phase shift or a minus gain somewhere in the feedback path, right? So I think this is clear. If it is not clear, please revisit this segment again. This will be uploaded in the YouTube channel, right? One chat problem is there. How you calculate multiple by 2? Sarvana Satish. I do not know what he is talking about. Multiple by 2. Okay. Yeah, please, Satish, please comment me or in the YouTube link also or in the discussion forum that what was that. If I missed something or you did not understand anything, I will surely take it up, right? So moving forward to problem number 4. What is the gain in the circuit shown here? Okay. Okay, this is pretty simple problem, I think. How do we go about these problems? As it is an ideal op-amp, I can simply consider this as to be this has to be first stage, and another thing I will analyze later, right? So this how I analyze this circuit. This is simply, let's say this point your voltage is Vx, okay? Vx, let's say, and this is your 10K, this is 2.7K, this is your 1.8K, right? This is your Vi, okay? So this remains Vi because no current is flowing into the op-amp because it is an ideal op-amp, right? And you can make yourself satisfied that this is in negative feedback in the same method I have discussed earlier. So this voltage will also be Vi. That means this point will also be Vi, right? So your Vx minus Vi by 10 is nothing but Vi by 2.7. So Vx by 10 is equal to Vi by 2.7 plus Vi by 10, or I can simplify my analysis. Let's say this Vi would be nothing but your Vx into 2.7 by 12.7. Right? This is a voltage divider. So you have 2.7 divided by 12.7 is your 0.212. Let's say. So your Vx is nothing but 1 divide 0.212 is 4.716 Vi. Okay. So I know my Vx, and let's move on to the next stage. So now I'll analyze this part. To 1.5K, this is V0, this is 8.2K, this is 1.2K, this is my Vx, this is nothing but 2.2K, right? This is positive, this is negative. So this is nothing but my virtual grounded because no current flowing inside. So this is also my ground. So my current flows this way. So Vx by 1.2 should be equal to 0 minus V0 by 8.2. What I did KCL at this node. Okay. So your V0 would be 8.2 over 1.2 into Vx and with a negative sign. So That is my 8.2 divided 1.2 is 6.83 minus into what is your Vx is your 4.716 Vi. So your V naught by Vi is nothing but this into 4.716 is equal to 32.226 minus 32.226. So your answer would be this B, right? Okay. So this is one way to analyze this circuit. In this regard, I want to mention something that suppose you have two stages, right? Let's say this is A1, gain A1, this is A2, this is X, this is Y. So you will write simply that Y equals to A1, A2 into X, right? This is called a cascade configuration, right? But is this always true? Can you always do this A1 into A2? Let me give you some circuit. Let's see, this is V naught, this is Vi, okay, and this is one, let's say this is 2, 2, 2, 2. Okay, so you will be tempted to analyze this as first stage, this as second stage, right? And let's say this is Vx. Okay, so if you let's say what you will get, you will say Vx is equal to nothing but this is Vi by 2, right? Vi by 2 by 4, that is Vi by 2. Similarly, V naught is Vx into 2 by 4, that is Vx by 2. That means your V naught would be Vi by 4, right? This is the same analysis I have done using the cascade thing, but this is not correct. Why it is not correct? It is not correct because let me just analyze the circuit in a different way or in a more conventional way. This is 2, 2, 2, 2. This is your V naught. This is your Vi, right? So this is open. So this 2 and 2 will be in series. So this will be 4 parallel 2. 4 parallel 2 would be 4 into 2 over 6. That is 8 over 6. That is 4 over 3 ohms, let's say. And your this voltage would be this Vx, say Vx would be Vi into 4 over 3. No, yeah, for this is 2, 2, 4, 4, 4, 2, 4 over 3. So this would be your, let's say it's 1.33 by 3.33, right? This two will be in series. So your Vx would be 1.33 divided 3.33 is 0.4 into Vi, okay? And your this is like that. So this Vx is between this to this, so it will be a V naught will be Vx by 2. That is your 0.4 Vi by 2 is equal to 0.2 Vi. And this is 0.25 VI. So this is your right option, right? Let me know if I made any mistake in the calculation, right? But this is the correct answer, and that is not. Why could not we use the cascade configuration? Because you see here my circuit, this is, say this circuit is loading my earlier circuit, right? This is called loading effect. So if there is loading effect present in your circuit, you cannot simply do the cascade operation as shown here. This is wrong, right? So how to, and when do you when you can use this same circuit, same cascade operation? Suppose I give you this and I use a voltage buffer here, right? Let's say 2 voltage buffer is a nothing but a voltage control voltage source with no in infinite input impedance. This input impedance is infinite looking in, and this just translate this voltage to this, right? So if this is Vi, this is 2, then obviously there is no current flowing. That means Vx will be Vi by 2. And similarly, as it is a voltage control voltage source, so with infinite input impedance, or it is a buffer, this is called a voltage buffer. So this voltage will also be Vx, and then you can simply write Vx, V naught is simply Vx by 2, and that is Vi by 4. This case it is right because you have used a voltage buffer. This is a voltage buffer. You see, in the circuit we have discussed, this was acting as a voltage buffer, right? Because no current it is allowing to go in at its input, and it is a voltage control voltage source. So it is offering you some kind of voltage buffer actions. So that's why we were able to use the cascade method to analyze the circuit, right? So this is very important thing, and this is used in IC design very often. So let's move on to next problem. Assuming that the op-amp operate in the linear region, what is VO, right? So first, two things. Linear region. What do we mean by linear region? If you have gone through the lectures of Professor Patil, you must have seen that this kind of configuration, this is minus VEE. Let's say my VSAT, it is less than VE minus VE actually, and it is positive VSAT. And this region is your called linear region, right? This is your linear region. And for an ideal op-amp with infinite gain, this is my diagram. So this is my linear region. Linear region, let me just simply, this is my linear region. So it's at a single point, right? And I have an infinite gain. That means if my op-amp is operating in linear region, I will have my ideal op-amp consideration intact. That means my gain is, what is the gain at this point? You see that dV naught by dVi is nothing but infinity, right? So that means is your gain is infinity. One condition is satisfied. Now I need to check whether I have negative feedback in place, right? So you see here you have two ways feedback, right? This side also you have a feedback, this side also you have a feedback. So how do you check whether you have a negative feedback? It's very simple. The same method we'll use. We will use the same method. This is grounded. So input will also be grounded. So this is my, let's say A, this is B, and here I will apply a V test. I have removed the OPAMP as the step one, what I have discussed. This is my V test. This is 91K. This is 8.2K. This is 4.7K. This is 12K. Right? So what is my VA? My VA is nothing but V test into 4.7 over 16.7, right? That is 4.7 divided 16.7 is your 0.28 V test, right? And what is your VB? VB is your V test into 8.2 over 99.2, right? That is your 0.08 V test, right? So what is your VAB? Is nothing but 0.20 V test. So your alpha is greater than 0. That means your A terminal should be negative and B terminal should be positive for the circuit to be in negative feedback, right? So this is negative, this is positive. Yes. So we have confirmed that the circuit is in negative feedback. Now we will apply the virtual short, right? Virtual short concept. So now if I simply copy this circuit, now if I simply copy this circuit, so what will I have? I have this voltage and this voltage same, right? Let's say this is Vx. So applying KCL at this node, I will have Vi is my zero point 0.4, so 0.4 minus Vx by 4.7 is equal to Vx minus V out by 12, right? This is one equation which I have 3 minus 12 Vx is equal to 4.7 Vx minus 4.7 V naught. So I have my 16.7 Vx is equal to 3 plus 4.7 V naught. That means my Vx will be 3 over 16.7, that is 0.18 plus 0.28 V naught. Okay, the Vx I got from KCL at one node. Now I will apply KCL at this node. This is also Vx. So 0 minus Vx by 8.2 is equal to Vx minus V naught by 91. So I'll have my V naught by 91 is equal to Vx by 1 over 91 plus 1 over 8.2. That is 1 over 91 plus 1 divided by 1 over 8.2 is equal to 0.133 Vx. Okay, so V naught is equal to this into 91 is equal to 12 Vx. Okay, so 12 Vx we know 0.18 plus 0.28 V naught So I have this 0.28, 12 into 0.28 minus 1, 2.36 V naught is equal to 12 into 0.18, 2.16. So your V naught would be 2.16, 2.36 around minus 0.91 volt. Okay. Did we have any option? Okay. We had, did I make some calculation mistake? Okay. Let's check again. This 0.4 minus Vx by 4.7, Vx minus V naught by 12. This is, oh, okay, this is your 4.8, right? So if this is 4.8, then this is 4.8. That means 4.8 divided 16.7 is 0.287, 0.287, 12 into 0.287 is 3.444, divide by 2.36 is equal to 1.45. Right. So this is your right answer. Right. So moving on to the next problem. In this problem number 6, in the circuit shown in the figure, what is the gain? So I know that this will be my ground, right? Because it is in negative feedback. Get yourself assured that it is in negative feedback in the same way, and it is having an infinite gain because we are considering an ideal op-amp. So I can simply use Vi minus 0 by 1.2 is equal to this. Let's say this is Vx, 0 minus Vx by 9.1. So Vi by 1.2 is equal to minus Vx by 9.1. So to get Vx, I will be applying KCL at this point. That means minus Vx by, this is minus Vx by 9.1 is equal to Vx minus V naught by 8.2 plus Vx by 4.7. So your V naught by 8.2 is equal to Vx by 1.8.2 plus 1 by 4.7 plus 1 by 9.1. So your Vx would be, V naught will be equal to 1 divided by 8.1 divided 8.2 plus 1 divide 4.7 plus 1 divide 9.1 is equal to this into 8.2 is 3.64. Okay, so Vi is 9.1 by 1.2 equal to minus Vx. So Vx is equal to 3.64. 3.64. Okay, so let's say Vx equal to here 9.1 divided 1.2 is 7 minus 7.58 Vi. Okay, put it here. So your V naught would be this into 3.64. So minus 27.603 VI. So your gain is nothing but minus 27.603. Okay. So this is your right option. So moving on to next problem. This is again this I need to find out I1, right? To find out I1, what do I need? I need to find out this voltage. This voltage, how can I get this voltage? This voltage can we get by this way? I can use this and this voltage are same, right? So let's say it is V naught, then minus 1, let's say it is Vx minus Vx by 1.8. I am applying KCL at this node, right? Equal to Vx minus V naught by 1.8. Right, so here minus 1 minus Vx equal to Vx minus V naught. That means your V naught is 2Vx plus 1. Okay. Again, if I apply KCL at this node, so you have this. This is a parallel combination of 4 and 2.2. That is 8, 4 and 2.2. That is 8.8 divided by 6.2, that is 1.42. So I have V naught minus Vx by 2.2 is equal to the current coming in should be current coming out of the total thing, that is Vx by 1.42, right? So V naught by 2.2 is equal to Vx by 1 by 2.2 plus 1 by 1.42. 1 divide 1.42 plus 1 divide 2.2. Okay, so wait, 1 divide 2.2 plus 1 divide 0.42, 1.158. So your V naught would be into 2.2, 2.55 into Vx, right? And your V naught is this 2Vx plus 1, 2.55 Vx. That means 0.55 Vx is your 1. That means your Vx is nothing but 1.81 volt, right? Then what about your this I1? I1 would be 1.81 divided by 4K. That means that milliampere is nothing but 0.45 milliampere, right? So D is your right option. It is nothing but KCL, simple KCL, right? Once you are assured that you have virtual short, then you can simply just use KCL at one of the input node and then again if required another input node, right? So then again this is a problem where they have mentioned I need to find out K1, right? So this is V2, virtual short applies. Condition, again I am reiterating because this is very important, that it is a negative feedback and the OPAMP is ideal. So this is my V2, this is my V2. So if I apply KCL at this node, V1 minus V2 by 5, that means current coming in is equal to V2 by 15 plus V2 minus V naught by 10. Okay, so if I V1 minus V2 is equal to V2 by 3, plus V2 minus V0 by 2. So 6V1 minus 6V2 is equal to 2V2 plus 3V2 minus 3V0. So your 3V0 would be this 8V2, this minus 3V1, right? No, this should be, this is also V2, right? 5. So this is my 5V2 and this is 11V2, right? And this would be minus 6V1. So your V0 would be 11 by 3V2 minus 2V1. That means this is my K1, this is my K2, right? So your K1 is minus 2 and your K2, I think in the next problem they have, yes, the next problem, same circuit, they have asked about K2. K2 would be 11 by 3, that is 3.67, right? So this is the right answer. Okay, so move on to next problem. For the circuit shown in the figure, what is V0? Right? They want us to find out V0. You see, again, it is in negative feedback and we are dealing with an ideal op-amp. So this is virtual short, that means this is 2. Let me just do it in this only. If this is 2 volt, then this is also 2 volt, right? If this is 2 volt, then there is no current flowing across this because this is also 2 volt. So this I can ignore simply. I need to find out this. So this is 2 volt and I can simply ignore this part of the circuit, right? So how can I solve this? I can simply solve it like 1 minus, okay, just let me increase the font. 1 minus 2 over 1.5 is equal to 2 minus V0 by 0.82. 0.82 is to be consistent with the units. We are dealing with all kilo ohms, right? So this current will be this current because no current flowing inside, right? So I am using KCL at this node. So simply this is minus 1 by 1.5 is equal to 2 minus V0 by 0.82. So 0.82 divide 1.5 and so I get minus 0.55 is equal to 2 minus V0. That means V0 will be 2.55 volt, right? So this is your right answer. Again, this is okay. This is the duty cycle problem, right? It's one of the duty cycle problems. Duty cycle I have explained. What do I mean by duty cycle? So you see the question is in the circuit shown, the op-amp operates in open loop configuration. Okay, the op-amp is in open loop. We can very sure that there is no feedback path between output and input. Okay, so what is the duty cycle D? If the wiper is in the top position, right? If wiper is in the top position, if it is in the top position, then that means this point is my grounded, right? If this point is grounded, that means this has nothing to do with this. So I will simply have this minus 0 at the output. So output will be simply the same waveform. Okay. And I can simply see from the symmetry that half of the time it will be on, right? So my duty cycle is 50%. By inspection, we can answer this question. So 50% is my right answer. Okay. So moving on to problem number 12. What is the duty cycle if the wiper is in the middle position, right? Middle position means I have a resistance of 1.1 K equivalent. So my circuit will be nothing but this, and I have this. So this is 1.1 K. This is 3.3 K. This is 10 volt. This is my V naught, and this is the input waveform, right? So what is this voltage? This voltage is nothing but this voltage 1 by 4, right? That means this voltage is 2.5 volt. So my output voltage would be this minus 2.5 volt is my V naught. This is plus 12 volt. This is minus 12 volt. So I need to find out what would be the duty cycle. How do I find out that? Simply just draw this. If minus 2.5, then this will be 2.5, and my waveform will be something like this. Okay, so this will be my minus 2.5. This is 0. This is V out. What will be this? This is minus nothing but 12 minus 2.5, and that is your 9.5, right? This is your 9.5. So let's say this is T and this part is T1. From the triangle property, we can simply use that. This is my 9.5. So 9.5 by the total is 12 is equal to your T1 by T, right? If anything you have might have these are the theorems which you have studied in 10th or 9th standard, right? Suppose this is a right angle triangle, right? And you get this, and the length of this is B, this is B1, and the height is A, and this is A1. So we know that A by A1 is equal to B by B1. The same principle I am using here. So my T1 is nothing but 9.5 divided 12 is 0.8 T, right? So what is my duty cycle? Duty cycle is nothing but T1 by T into 100%, right? That is just wait a second. This is my, oh, okay. This is not T1, right? This should be, yes, this is T1 by T. Okay. This is 2T, right? Your period is, entire period is 2T. So this would be 0.8 by 2 into 100%. That is your 40%. Okay. So your duty cycle reduces as your wiper steps in the middle of the resistance. Similarly, in this problem, they have mentioned that wiper is at the bottom position. That means I can assume there is no wiper. This is a simple circuit, right? It is in here means it is the wiper has no action. That means the potential at this point is nothing but this is a simple voltage divider, 10 into 2 divided by 5, that is your 4 volt, right? So again you have this kind of waveform. So here now This is your T, this is your T1, this is your 4, and this is your 8. Okay, so your 8 by 12 would be equal to this height divided by the entire height divided by the entire height is equal to this T1 divided by entire T. That means your T1 is nothing but 0.67 T1, 0.67 T. So your duty cycle would be T1 by 2T into 100% is equal to 0.33 into 100% is nothing but your 33%, right? So A is your right answer. This is pretty simple problem, just you need to understand how the wiper works, right? This kind of thing you can say this is called some auto changing, right? This you will see in auto transformers, right? In railways you will see there are certain in between some block section you use between two station we call it block section, you use certain kind of transformer to just simply it use as a regenerative repeater, you may say. So this kind of auto transformer, what they have two coils, right? The secondary coil, it has a auto tuner, auto wiper, right? It is automatically adjusts the according to the load, it automatically adjusts the number of turns in the secondary coil, right? So this is in similar sense. This is a auto adjusting wiper. This can be manual or this can be auto also. Generally, this can be auto. So I am just telling you the one of the one of the cases where this kind of things are used. Okay. So moving on to the next problem. Okay, this is pretty simple. They want us to find out what is V out. Okay, how do you find out V out? You see that it is in negative feedback, it is ideal. So this is ground. So simply 2 minus 0 by 4.7 is equal to 0 minus V naught by 1.2. So your V naught would be 2.4 by 4.7 minus, it will be around minus 0.51 volt, right? Because 2.4 into 2 is 4.8, so it denominator is somewhat reducing, so it will be somewhat more than 0.5 volt. So from the options we can see that it is minus 0.51 volt, right? So moving on to the last problem, they want us to find out this I1, right? So how do I find out this I1? I know my V naught, so I will use simply KVL in this loop. So 0 minus V naught. What was my V naught? V naught was my minus 0.51, right? So this is minus 0.51 volt. So 0 minus minus 0.51 divided by 1.2, this in current plus I1, this current is should be equal to minus 0.51 divided by 2, right? So my I1 would be nothing but minus 0.51 by 2 minus 0.51 by 1.2. So it is minus 0.51, 1 by 2 plus 1 by 1.2, and obviously it is in milliampere. So it is 1 divided by 2 plus 1 divided by 1.2, this into 0.51. So it will be minus 0.68 if I'm not wrong. Okay, so this is the right option. So we end this session here. Please tell me if you have any query, or you can use the discussion forum in the ask a question window in the course web page, or you can comment in the YouTube link which the NPTEL team has shared with you. So that way I can get back to you if you have any query, right? So I have some time. If you want to ask something, you can just ask me the questions, right? See, I spend more of the times in the concepts because these things are pretty much important. You know, how do you determine the signs of the OPAMP when it is in negative feedback or if it is in positive feedback? Because this will help you to attend the questions in GATE also. In GATE, they ask these kind of questions. I'm not sure about the current syllabus, but these kind of concepts will help you in circuit designs also. You know, if you want to pursue your career in IC design or in VLSI domain, then you will definitely need the concepts of this negative feedback. And the negative feedback is basically the most essential thing in the IC design, I would say, right? So let me stop the discussion here. If you have any question, you can ask on the discussion forum, right? Thank you for participating. That's all for today.